So I think I'm going to start with the fundamentals of PDF because I feel there are some knowledge gaps that probably I want to fill before we can really be confident with processing the PDF data. And still, my philosophy is I don't want to go with the black box approach and simply just saying input this command and get this, and input that command and get that. I feel that is may not be very helpful. So uh, knowing some of the fundamentals, I think is important and will help us actually to do the analysis independently. So in the future, I'm sure you will deal with some specific scientific cases, and before we can discuss about it, you can think about them independently using the knowledge about the PDF you have. Uh, at the very beginning, I think we need to have a change of notion. I think everyone is very familiar with XRE, and probably the classical picture is still the Bragg's law. And a lot of times people will talk about the X-ray shining on this the plane of atoms, and then we have the either the constructive interference of their destructive interference of outcoming X-ray. So when they are constructive, then you would have the peaks. And then you can use this kind of a simple geometry argument to derive the Bragg's law and say, okay, oh, then we know how the despacing is related to the Bragg peaks position. Uh, well, this is definitely very intuitive and also helps a lot for understanding the diffraction phenomenon. But uh, I would say this is too simple a picture and doesn't really help if you want to go further, even for the XRD analysis. And what I mean by that is one thing is intuitive, and strictly speaking, uh, with all respect to is Nobel laureates, since it was actually proposed by Bragg's father and son, and they're the famous Nobel laureates. But this picture is not physically correct, and so uh, the real if actually there you start digging more into the physics about how the approach of dealing with diffraction, you'll realize actually it's more always based on the scattering picture, which I'll show in the next slide. And the pitfall of this kind of a plane reflection is that uh, I met several people who think um, intuitively that they would think, okay, if I have heavy atoms sitting on these planes, then I have the strong peaks, right? So since they're strong scatters, and in fact, some of the papers in some of the high-profile journal, I saw one paper from Anguwan, actually about the battery paper, and use this kind of an argument to discuss how the intensity of XRD peaks change. And I think that's probably a common issue. So I just want to bring it out here, bring it to your attention. And this is not correct. And you probably have already known that the intensity relates to all the atoms in the unit cell and their positions. It has nothing to do with what atom is sitting on what plane. There's no such a relationship, and it probably is counterintuitive if you resort to this kind of a reflection picture, right? And also, it cannot bring us further, and probably just help tell us, okay, well, where's the position of the peaks? Then what's next? And very likely there's nothing left. But the power of XRD is really to solve the structure and tell us what kind of atoms we have and where they are. That's the power of the X-ray diffraction. So we need to change of the notion, right? I don't want to say too much negative things about Bragg's law, but we need to change. So we need to switch from the Bragg's law picture reflection to the scattering picture. And we are all aware that the X-ray itself is a wave, so it has it's also treated as a vector. So sometimes we would refer to the wave vector, and which is typically denoted by the k. And also this is relates to, their absorption data. And we typically talk about the K space, right? So K is also a measurement of their magnitude of the momentum, the wave vector. So we need to think about the coming X-rays as waves, and they have the wave vectors. And when they are scattered by the electron, if this is elastic scattering, which means that the energy is conserved, then there's no energy loss, and the outcoming the X-ray, the wave vector, it still has the same magnitude, but change the direction. And this kind of a change direction is shown in this kind of illustration. So we see this is incoming one, and this is a diffracted one. The length is the same, but the directions change, and they do have this kind of two-sided relationship. And this kind of two-sided is the geometric two-sided that we normally get from the XRD measurement. And because of this kind of a momentum change, and we have this kind of a vector indicating how much is what is actually the diffracted what is the scattering vector, which is the difference between the incoming one and outcoming one. So this is termed as the Q vector, and this is very important. This Q vector is really the fundamental picture for us to really to understand the XRD and to really understand the PDF. So we always need to come to this scattering picture when we talk about the detailed the details of XRD in the PDF. And this is very useful. So one thing is, for example, it directly tells us when the diffraction occurs. But surely this is a simple relationship, but the process of reaching this kind of a relationship is not trivial. So it involves the concept of reciprocal lattice. So we need to use the tool of reciprocal lattice, and then we need to understand the vector analysis. And so there's some standard mathematical derivations telling us how this conclusion can be reached. But this conclusion is saying that when the diffraction occurs, only when the scattering vector, this Q, is also a vector in the reciprocal space, so which is depicted by this G. Only Q and G, they're both in the same direction and also in the same magnitude. Only when this occurs, where a diffraction phenomenon occur. So this is really the essence of diffraction, relating this Q, the scattering vector, with the reciprocal space vector, which is G. So you can see this G is the HKL dependent. So it relates to the HKL planes, both the direction and the d-spacing, which is also contained in this G vector. Its magnitude is actually d-spacing, by the way. And also this picture is the basis of solving the structure. What I mean by that is that solving the structure has been going through a long way from actually people started analyzing scattering from electron, a single electron, then from atoms, which is mostly by the valence electrons. So I think in the later XRD or some other lecture series, I'll describe more about this so we can understand how the scattering from electron from atom is contributing to the XRD intensity we see. And then we can make the model more sophisticated, actually making a whole array of atoms, and even with the 3D periodicity, and so we have the lattice. So then we talk about the scattering of atoms from the lattice. Then we reach the structure factor, which is actually correlating the intensity we collect and all the atomic positions in the cell that we have. So we establish this kind of correlation. Then we solve the structure. So using this kind of mirror intensities and resulting to the structure factor, we want to identify the locations of the atoms. That's basically solving the structure. So, and all this whole thing is based on the scattering picture. And the last one is very, very relevant to what we discussed today. This is a scattering picture is also the language for PDF. So there's no way to talk about PDF if we start with the reflection, the picture. So it always starts with scattering. And so you probably will encounter a lot of terms uh, related to scattering when you read the PDF papers. For example, diffuse scattering, people would talk about, okay, this is diffuse scattering, very weak, and it's much weaker than the Bragg scattering. And people will say, oh, okay, PDF is a total scattering technique. And also, if you go to neutron, it's very likely people will talk about the neutron scattering. So all these kind of things resort to this scattering picture, and that is really the language for the PDF. And I also want to give you a flavor of the history of PDF. So I think the PDF itself, in fact, evolved a long way, starting from the early 20th century, more than 100 years ago. And already from those phases, you can see the history of PDF is actually a bunch of famous figures like Debye or Zernike. Actually, Debye and Zernike, they're both Nobel laureates. And Warren is somebody, if you do not do diffraction very often, you're probably not very familiar, but there's a very famous award in the diffraction community, which is a Warren Award. It's kind of like the highest award for the diffraction. And those are all very big figures. And this lady showing in here, so probably you can recognize as Rosalind Franklin, and who actually made a significant contribution to discovery of the DNA structure. So these are all very active, very famous figures in the different community. I think is you might as well know for some kind of scientific background. So I think the whole thing should be started with Debye, and that's well acknowledged. Debye has a very sharp intuition, and instead of actually correlating the intensity with electron density, which is actually our XRD approach, Debye realized that, in fact, intensity that would matter, in fact, is actually the function of all the atomic distances in this system. So, which is depicted by this RMN. So that is basically saying, if we have a certain set of atoms and they have their own positions, they will have their own set of atomic distances. And this will determine this actually the scattering intensity. So this is a very different approach from the approach of XRD. And so also sometimes their philosophy of the PDF is also termed as their Debye equation philosophy. So it's different from their XRD philosophy. And then about 15 years later, Zernike and Prince, they independently derived this equation, which is very important. It's showing us there's a relationship, and this is a Fourier transform relationship. So we can see the sine function here. So typically, if you have sine of the exponential of e, or the cosine actually is an indication of the Fourier transform. So you might as well want to spend a little bit of time understanding the Fourier transform process if you are not very familiar with that. So they pointed out this Fourier transform relationship between actually the intensity and this kind of their atomic density. So this is our rho A is a kind of average atomic density. So that's basically saying how much their atomic density deviates from average one is actually has this kind of Fourier transform relationship with the R. And then gradually there are some even some PDF experiments. So one was started by Warren back in 1936. He was the first one to measure extra PDF molten sodium. And the data quality, cannot compare with what we have today, but he did actually correctly got at least the first the sodium the correlations in his data. And at that time, doing Fourier transform is very tedious, and typically takes several hours, if not days. So Warren was a MIT professor at that time, and he was very capable, and he did all the whole thing by himself. And then there was actually the actual PDF of disordered carbon, and that was done by Rosalind Franklin in 1951. So she's also a very capable lady. So doing the actual PDF using the lab source X-ray, and also deriving, processing all the data by herself. At that time, this is really something very challenging. Um, but I think everything changed once we have the synchrotron and the computer. So with the synchrotron, we have one thing is we have extremely high flux, and the other thing is we have a very high energy, and we can have a very short wavelength, and both of which actually enable us to get a very high Q. Oh, I think I must apologize. I didn't point out some numerical relationship. So this Q actually should is related to both the lambda, the wavelengths, and the two theta. So the actually you can just search, and there it's very easy to see. Sorry, it's very easy to see the magnitude of this Q. So it relates to the wavelengths, and the shorter the wavelengths, the larger the Q will have. So by using the very short wavelengths, then we can reach very high Q. And also with the very high flux, we can get a very high, very good signal to noise ratio, even at the high Q region. And this is not something trivial. And this is something that is critically needed for obtaining a high quality Q region data for the Fourier transform. As we know, because Fourier transform, in fact, mathematically speaking, Fourier transform involves from negative infinite to the positive infinite, right? But in reality, we cannot afford to do that. So we want to have cover a high Q range, a range that is as high as possible, such that we can have a meaningful Fourier transform. So also that's the motivation why we always want to pursue high Q, because the better high Q you get, the better high quality of Fourier transform you will get. And also the computer, and this is also something very helpful to the PDF development, because with computer, we can simply compute the fast Fourier transform in a matter of seconds, compared with the old days when Warren actually was using the instrument to compute the Fourier transform at least for several hours, and even for days. So I think it's both a process of the theoretical advancement and also the hardware advancement, especially synchronous computers, so that today we can routinely measure total scattering pattern and do the Fourier transform to get a PDF. And we probably would gradually take it for granted, but actually there's some a long history behind that. Okay, this slide is from Professor Simon Blanch's slide. So I simply just copy and paste, because I feel this one really captures what we need to pay attention to, and also points to something we probably take for granted at the beginning. So we are probably accustomed to the diffraction data when we see some small peaks at a very low 2 theta, and gradually everything dampens out at high Q or at a high 2 theta, but we better use Q from now on. We do not talk about 2 theta. At very high Q, looks like everything is flat, and this is a FQ and a square. This is actually the average scattering power computed under this formula. So we can, using this formula, we can compute the average scattering power. So you basically see everything falls out. So looks like there's nothing much we can get from this high Q region. But this is not true, because we are talking about the data processing later. We'll see that this FQ, which is the function that is really Fourier transform, in fact has a lot of structural features at high Q. typically, let's say at this 20, at this 16, we have to still have this kind of oscillations that comes from the structural features. And those things are very, looks like very trivial if we just look at the diffraction data or the intensity data. So that spells the importance of getting high Q data. Also, patiently measuring your sample if a sample is a weakly scattering, and just to try your best to get some high Q data here, then you have some chance of getting the unique structure information after doing the Fourier transform. And in terms of software, I think I just want to mention there are a bunch of other softwares, but mainly we're using the software from Professor Simon Billing's group. So this one is a PDFgetx3. It was developed relatively long time ago, and that one requires lots of experience. So at a certain stage, when you feel you are very confident about PDF processing, you know every detail of all the steps, you know what you are doing, and you're confident about all the sample information you have, then PDFgetx3 probably is the software you want to use, because that will provides you a lot of tailored the functions that you can specify according to your own will. So this is probably some software for a later stage. And PDFgetx3 is a much more user-friendly software. It's very friendly to beginners. So even before you really get to all the details of PDF, you can start using this software. And chances are you're doing the correct thing, because normally the data from the PDFgetx3 has been verified there. If treated properly, they are basically the same as from PDFgetx2. And this is also the ideal software that we can start with to learn how the PDF data analysis is carried out. Okay, and we will plot these figures later when I ask you to input the diffraction data from the fit2D. So this is basically the fit2D, the data from the fit2D. You get a raw image, and you use the procedure we discussed last time. Then you arrive this kind of intensity data, which is basically the intensity as a function of the two-seaters or the Q. And then we have this kind of a SQ, so which is shown here. So this SQ is a function of Q, and it's defined in this way. And okay, I think I probably still better explain a little bit about this notions. So IM stands for the measured one. So this is kind of like a measured intensity we have, and this is what do we have here. This is measured intensity and something you get from the fit2D. And this ICQ, this is also intensity as a function of Q, and C stands for coherent. And so we need to understand that the scattering picture we previously draw is based on actually the elastic scattering. And also for the PDF, it should be elastic and coherent. So elastic meaning that there's no energy loss, such that is called elastic. And coherent simply means that the outcoming waves, it should have the same phase. So that's the definition of the coherent. And the PDF, in fact, also the diffraction, X-ray diffraction, only uses this fraction of the outcoming the X-ray, which is coming from the coherent and elastic scattering. So that's the information we need, and only this part really relates to the structure information. But the measured intensity does not just include this part. This part is dominant, but it also has some other contributions. For example, this kind of a BQ. B stands for background, because where X-ray shines on a sample is doing a lot of things, not just the coherent elastic scattering, but also it has the coherent inelastic scattering, and has incoherent elastic scattering, and has incoherent inelastic. All this kind of scattering actually is counted into the total intensity you measure. And that part has nothing to do with the structural feature and will not help you anything about solving the structure you want to understand. So this part needs to be dealt with, and especially, for example, the competence scattering. So I will show in the next slide what this kind of background really looks in a sample by giving you some examples to give you some idea. So we want to get rid of that, or at least we can. We hope to deal with them properly. And also, we have this AQ. AQ is actually basically a coefficient, but this coefficient is a function of Q. And this coefficient comes from several origins. For example, your sample, in fact, also has some kind of absorption, right? So, so when X-ray hitting a sample, part of X-ray is in fact absorbed. So actually, that would, in some degree, dampens out this kind of a coherent elastic scattering that you will see. So there's absorption issue. But for high energy, absorption typically can be neglected. So think about it. When you are hitting your X-ray with your sample with X-ray with a wavelength of typically 0.18, which is really high energy. And for us, if we measure simply the transition metal oxides, they're basically almost transparent, in the eye of this such high energy X-ray, with a very small amount of absorption. So, but anyway, this absorption comes into play, and also there are some other processes such as multiple scattering. And for the scattering, typically we discuss is actually a one-order scattering, right? A single scattering event, but there can be a multiple scattering events that will also dampen out the intensity you will see. And also, in fact, the X-ray is polarized. So we need to understand that in principle, synchron X-ray is actually has a polarization factor of 1, meaning that is actually the electromagnetic wave is only one plane, is constrained one plane. It's not actually dispersed in all the planes, but the true polarization factor for synchrotron typically is about 0.95 or to 0.99 something. So if you remember last time's lecture, we do encounter a scenario in which we need to input this number. So the software would ask us to input the polarization number, so which is typically 0.99, is very good for NISOS 2. And so, but for lab X-ray, so typically you probably get 0.5 or 0.6 something. So this kind of polarization factor would also come into play, that would adjust your intensity. So keep those things in mind. That's the origin of AQ. And this, so I think I explained the other every single component in this equation, and then we derive the SQ. So we already see that SQ is a strictly structural function. It only utilizes the IC part, the coherent elastic part, and this part is actually further processed with this FQ average. This is basically saying the average scattering power of a sample. So let's say we measure lithium oxide. Then we know the ratio between them is 1:1:2, right? So with that kind of ratio and the other atomic elements, we can compute the average scattering power of your sample, and those terms are actually come into play in this equation. So once you understand this equation, you know the necessity of getting some knowledge about your sample formula, right? Sometimes when we collaborate with people, they're reluctant to tell us what exactly the sample they have, but we have to tell them, if you do not tell me the formula, I cannot process this data for you. So just keep that in mind. So next time you measure your sample, you really need to understand what are the chemical species in your sample. And because those information would come into play in this equation. If they're not accurate, actually they will influence the further processing. So that's SQ, and FQ is basically a very variant of FQ of SQ. And why we want to compute that? Because this FQ is in fact the real function that is doing being Fourier transformed, right? So Zernick and the Prince actually pointed out actually there's a Fourier transform relationship between the merit intensity and the atomic density, which relates to the PDF. But in practice, it is this FQ, which is function of Q and SQ, that is really being Fourier transformed. So normally the software always compute this step and then carrying out the Fourier transform on this FQ function. Then we'll get this GR, which you see here. And also by learning these functions, you would immediately see this SQ should approach 1 as the Q goes into infinity, which is all the case here, right? You see this SQ actually, when we go to very high Q, it's getting close to 1. And this is the limit of this equation. And likewise, the limit of FQ should be 0. So you will see FQ when it goes out to a very large Q number. So we see the FQ is approaching 0. And also that's knowledge you need to have when you try to adjust the processing parameters to see which parameter configuration would give you the data that makes most sense. And finally, this is the GR that we want. And typically, this is what we show in the paper, right? We have this GR telling us directly the correlation between this pattern and atomic pairs. So for example, this is about the 2 angstrom, indicating that we have this kind of a 2 angstrom atomic correlation, which corresponds to transition metal oxygen. And we have this 2.8 something, which is transition metal. But you do actually see some of the small peaks here, right? It looks like they do not have some a clear physical origin or some clear atomic correlation. And this comes from the Fourier transform process. So like I mentioned, the Fourier transform we do is in a limited Q range, right? So we only goes about 22.5 Q something in this case. So it's quite a large Q range, but still limited compared with the infinity, which is the ideal Fourier transform region. So the Fourier transform produce ripples, and probably this is also something reminiscent of the exact data processing. So when you process the X-ray absorption data, and also you would have some Fourier transform ripples at the lower region. And so how to deal with this part, we probably will spend some time explaining in depth how you should choose your parameters in an educated way, such that actually you do not miss out information. So for example, you do have some low R peak, then how do you make sure it is not a Fourier transform ripple, but rather some real substantial peak that's really belonging to a system, is some kind of structural feature. As I think that probably needs a separate lecture to discuss about this detail. At present, we can be satisfied that, okay, we get this kind of a general GR data having us telling us correlation between some of the atomic pairs. And this is actually a description about the previous the arm, this one. So as I mentioned, the merit intensity has some relationship to this part that we really want. This part is strictly structure dependent, and this BQ part has nothing to do with structure. So this is merit. This is what we want. So we need to deal with other parts properly. And this is basically showing the merit one is in fact the coherent and incoherent sum together with some coefficient multiplied, including for example, something I already covered, like multiple scattering, self-absorption issue, X-ray, polarization correction, all these things. And also there's a background, which is typically the incoherent disparity. For example, inelastic scattering, for example, there are competence scattering. For a sample that typically you measure, you very likely you will see something like this. So if you measure your sample and at XPD, you want to measure the background, right? Using the capillary. So typically this is total background you will measure. So this comes from both air scattering and the Kapton tube scattering. So we see Kapton tube is contributing about to this kind of differences, and there's a lot of contribution for air scattering. And what that means that is if you have very weak scattering system, you probably want to further minimize this part. You want to decrease it, and how to do that? You want to shorten the air scattering path. So this is also a practical issue. So for example, at their APS, their 11IDC, actually they have a very long walking distance, meaning that their X-ray has to travel a long distance to reach the sample, generating a lot of air scattering along the path. So they're actually they have a project which is to shorten this scattering path so that you can minimize the contribution from air scattering. And also you want to minimize your contribution from container, right? This example used the borosilicate capillary, which gives some, I would say, a relatively strong contribution. If you use a polyimide, and that their contribution can be minimized further. And also that's the reason we prefer to use a polyimide, the capillary, which has a very small contribution to the background. And that would be very helpful if you're dealing with some weak scattering samples. And this one is showing basically some other contributions for us to get an idea what kind of background we're dealing with. So this is actually example is aluminum tin oxide. So this is a mirrored background, and you see how much absorption and polarization and multiple scattering, complex scattering is contributing. Actually, they are contributing at a very low level. So it's basically, you do not see anything owning the origin looks like a straight line, but actually it's not straight. They're very minimal. So we can zoom in by plugging the y-axis in terms of the log. So you can see actually the competence scattering is still contributing somewhat to the total intensity, right? So at least, and the competence scattering is more dominant at a high Q. So you see the kind of increase, and you have competence scattering contributing high Q with the counts around several, maybe let's say 30 or 40 something. It's still very small compared with your own intensity, but because at high Q the data is important, and also the high Q, the scattering, the sample, the coherent and the elastic scattering is already very weak. So even this kind of a small background contribution needs to be dealt with properly. So in general, you see, you get an idea of that we are dealing with some very small intensities from like competence scattering or multiple scattering and these things, but still they need to be treated properly. Okay, I'll save the next slide for the next time. So I think that's pretty much the in terms of slides. I want to switch to the software. Today, we'll not go to a lot of details about software, but it's more like relating to what I just presented. So I stop sharing and switch to my software. So does everybody have their PDFgetx3 correctly installed? If you do, can you raise your hand? Oh. Okay, I only see Shar and Xiaoyang. Okay.
I do have it, but I can't. I don't know how to react when
okay.
Zoom, but I do have it. Yeah.
Okay, that's good. So at least we have 3 people, or maybe 4. Okay, I guess maybe everybody has succeeded in installing the software. That's great. So can you open your software? So what we do is you go to the directory that you saved your two files that I gave you, right? One is background, the other is MC622. So you press a shift, and at the same time you right click your mouse, you will see an open PowerShell window here. So I'm going to share that window to you. Let's say. Can you see my screen?
Yes.
Okay, great. Yeah, because after screen sharing, sometimes I cannot see your reactions, so you may want to just shout it out. We can type the comment, but I'm kind of a lazy guy, so you probably know this trick that you can simply use the arrow up and down, right, to directly to pull out the previous comment you used. So you can either type this comment by yourself, or if you have already did so in the past, you can use the arrows to bring them out. Then I think I may need a little explanation here. So this PDFgetx3 is basically saying that you want to use this, this program, and this -c stands for the configuration. So sometimes you can save all your configurations in a separate file, then you can cite them. But this time we're not trying to cite anything, so we just say we do not use any configuration file. And the -wave, W stands for the wavelength. So you need to know what kind of wavelengths you're dealing with, right? So for the XPD, this is a typical wavelengths and they are using, but their specific numbers can vary, especially the last two digits. So always make sure you're using the correct wavelengths. Otherwise, your data will be distorted. And -B stands for the background, with just instructing the software what kind of a background file we'll use. And this is the background file we'll use. This is a BCK, stands for background 75 OD. And so this kind of a capillary information that I put in just to remind myself of some of the specific background I use. And this is a 5-minute measurement. And so put our background file here, and then our sample information here. So this is the sample we want to deal with, right? So this is simply for educational purpose. So we use a very nice data, AMC622 and Princeton and .chi. So this is what we will process. And then this here comes the composition that we need to input. This is required. So if you do not input this one, the software will complain and we will not go further. And also this relates to the previous slide I just discussed, right? You remember in the equation for SQ, we needed the average scattering information. So which this actually tells the software, this is the average formula. Then the software will compute the average scattering power from this. And we'll touch upon this later. You will know that this average scattering actually also is a function of Q. So it's not a simple number, it's actually a function as a function of Q. So, and this kind of formula is needed for software to compute the average scattering power. And then we're just telling the software what kind of plot we want to see, right? Here, I'm basically listing all the relevant, the plots. The IQ is a measured one, SQ and FQ and the GR. And sometimes if you're already familiar with this processing, probably you just want to look at the FQ and GR. The FQ is the function that is really for a transform, and the GR is the final data get. So sometimes you can ignore this too. But here, for educational purpose, I'm listing all of them. And enter. Okay. Do you guys see a screen popping out having the 4 subfigures?
Yes.
Okay, great. So I assume everybody else also see that. And you already see their 4 subfigures, right? Because I can only share one screen, so I want to stay on this command screen. I do not want to switch to the plot figure. But you can see all those figures, and they are same in the slide that I showed you, corresponding to the IQ, SQ, and FQ, and the GR, right? Today, I think we probably will end in just several minutes. And before we leave, I just want to show you this comment here, because I already typed it before the lecture, so I still want to go through the easy stuff. You can type in PDFgetr.describe parentheses. Yeah, so you can type that and enter. So what is this is basically showing you what has been done during the data analysis. When we process the data, we're basically inciting this, this kind of this procedure of command, and here it describes all the steps it goes through, and you can see here what has really been done in the software. Right, so it's basically doing these things. It first transform the two-seater data to QA. So that's why I remind you, when we dealing with the Fit2D, do not choose the Q space option. Right? Do not choose the other options. Always choose a two-seater as the way to output the data, because here it will actually use the two-seater and it generates the Q space data. So if you have Q there in the Fit2D, then you actually would have a ROM data in the Q space. So two-seater in Fit2D, and the software will transform that to Q for you. And then it will transform to the grid regular. And this is basically defining the data range. One thing is to fit a polynomial to mimic the background. So I talked about that. You have the background, right? You have the, let's say, the competence scattering, which is sometimes cannot be strictly measured. Then you have this kind of the absorption issue, optimization issue, that is actually adjusting your intensity, right? So all those things are dealt with in the PDFgetx3 by a polynomial fitting. And this is not something, maybe not something strange to you, because if you have already done exact fitting or exact processing, you remember that in Asana, you always also ask you for a spline range, right? It will also ask you for a spline range, define the K minimum and the K max. That's basically, it's also using a polynomial to fit to the background. It's a similar philosophy here. So it asks you to define this region that the software will carry out this polynomial fitting to remove those contributions from, for example, the competence scattering, those issues, so that you can get a coherent elastic owning intensity, which is really useful for the structural analysis. And then you will transform the background. That's basically just the background, the subtraction. That's the file we used, right? So that's why we need to input this file in the beginning, telling us we have already measured background. So so the software do not have to worry about air scattering, the container scattering part. Those parts are strictly experimentally measured, so they can simply deduct it from their total intensity. And then we have this transform X-rays, and this is basically the getting your composition information, right? So to compute the average scattering power of your sample, and that needs to be normalized further in the SQ and FQ equations. And then we have this transform SQ, right? This is what I mentioned. So actually, the software will fit your SQ with a polynomial. We'll discuss about this polynomial next, because it relates to some of the parameters about the PDF processing. And then transform SQ to FQ. So we know that FQ is simply a variation of SQ, but FQ is more useful because FQ can directly for a transform. Then it transforms from FQ grid, because in the measurement, this FQ is not evenly sampled. But to do a fast Fourier transform, it always relies on equally spaced the sampled data. So it's basically resampling FQ to get a regular grid, so such that every point is evenly spaced. And this is getting preparation for the faster Fourier transform. And last but not least, you do the Fourier transform from the FQ to the GI. Then that's finally the GI you will get. Okay, I think we probably just end here today, and we can go on further for the next lecture.